Hello, everyone, and welcome to our webinar about testing for normality. And just before we get into the webinar, I'd like to present this information about additional support in case you're interested in additional support or services outside of this webinar. So we do provide full support for dissertation and statistics consulting. So if you are interested in additional, more one-on-one support outside of this webinar, you can use this information to contact us and get more information about the services that we provide. Okay. So first, I'll just give a brief overview of what we're going to be covering in the webinar today. And first, we'll talk about what exactly normality is and why it's important. And then we'll talk about different methods for testing normality. So we'll talk about inferential methods, descriptive methods, and visual methods, and go over each of those, how to test in those different methods, what the advantages and disadvantages are of each method, and how to interpret those tests. And then we'll discuss how to address non-normal data. So we'll discuss, if we run these tests and find that our data are not normal, then how do we address that in our statistical analysis? And then finally, we'll have time at the end for questions. So if you do have questions, you can feel free to type those questions into the questions section. And then at the end, any questions that aren't answered during the course of the presentation, we can take some time to answer those questions, but we will be saving all of those questions for the end of the presentation. So let's start off talking about what exactly normality is and why it's important for our statistical analysis. So a normal distribution is a distribution in which the most frequent values are near the center or the mean of the distribution, and values farther from the center are less common. Or in other words, a normal distribution is one in which the values cluster close to the center or centered around an average, and then they gradually get less and less frequent as you move away from the average or the center of the distribution. And it centers around the distribution in a symmetrical manner, like we see in the histogram at the bottom of the slide, which we'll be talking about histograms more a little bit later. We see an example of an approximately normal distribution that's centered around a score of 100. And so why exactly is normality important? Well, normality is important because many parametric statistical analyses, such as t-tests, ANOVAs, linear regressions, and others, often come with an assumption that the data follow a normal distribution. Now, this could be that the variable itself, like the dependent variable or the independent variable, is normally distributed, or it could be an assumption about another statistic derived from the data that's normally distributed. For instance, if you're conducting a linear regression, there's an assumption that the residuals of the regression follow a normal distribution. So another thing to keep in mind is that it's not always as simple as, is the dependent variable normally distributed? Sometimes it has to do with another statistic, but it's still equally important to test if those things are normally distributed, if the specific statistical test has that as an assumption. And so severe deviations from normality, if a test assumes normality, may affect the accuracy of the results. So if you try to run a t-test or an ANOVA on data that is very highly skewed or not normally distributed, the accuracy of that t-test or ANOVA may be reduced, because the data are not normally distributed. That being said, these types of tests, such as the t-test or the f-test that the ANOVA is based on, you may see some citations that claim that these tests are robust towards deviations from normality, but severe deviations may still affect the accuracy of the results. So it's still important to test normality in these cases. So now that we know what normality is and why normality is important for our statistical testing, let's talk about the different methods that we can use to actually test for normality. And first, we'll talk about inferential methods. And what we mean by inferential methods is that these are methods that use an actual significance test to determine if the data are statistically significantly different from normal. And the most common inferential tests that we have to do this are the Shapiro-Wilk and the Kolmogorov-Smirnov tests. Now, both of these tests are pretty similar to each other. And if you run these tests on the same data, you'll probably get similar results. There are some subtle differences between the Shapiro-Wilk and the Kolmogorov-Smirnov tests. A lot of people will prefer the Shapiro-Wilk. One of the differences is that people think that the Shapiro-Wilk has a little bit more power for detecting deviations from normality. But the two tests are pretty similar to each other. And again, these tests determine if the data distribution is statistically significantly different from a normal distribution. And so you would interpret this just as you would interpret the result of something like a t-test, where you're testing to see if two groups are different from each other. Well, in this case, instead of testing to see if two groups are different, you're testing to see if the data that you have are significantly different from what we would expect to see in a normal distribution. And so we can run this test, and it gives us a p-value that we can interpret. And so if that p-value is less than a specified alpha level or cutoff, so for instance, 0.05, then that would indicate that the data are significantly different from a normal distribution. So in this case, we actually would prefer not to see significant results for our Shapiro-Wilk or Kolmogorov-Smirnov test, because that would indicate that the data are different from normal. And so there are some advantages and disadvantages to these inferential tests. The advantages to the inferential tests are that they are objective and easy to interpret. So they give you a p-value, and then you can interpret that p-value and make an interpretation or a determination of, are the data significantly different from normal or not? It's a simple yes or no determination based on a p-value. However, the disadvantage to these tests is that it only gives you that yes or no answer. It does not give you any information about the actual shape of the distribution, the severity of the deviation from normality, or any other information about the nature of the data. And another significant disadvantage to these tests are that they tend to be too sensitive with high sample sizes. So like any significance test, the higher your sample size, the more likely it is to be significant. So if you have a very high sample size, then even the tiniest deviations from normality are going to be detected as significant by these tests. So once you get beyond, 1 or 200 participants in your sample size, these tests will almost always turn out to be significant. And therefore, at large sample sizes, these tests are much less useful or meaningful. And so just to give you an example of what this result might look like, So here, and I did this in our intellective statistics software, I ran a Shapiro-Wilk test on a number of variables here, but the problem is that my data set has 1,000 participants in it. So this is based on a sample size of 1,000 participants. And so we see that all of these variables end up with a p-value less than 0.001. So all of these tests are turning out to be significant. So in this case, our Shapiro-Wilks test is just telling us that, across all of these variables, they're all different from normal. But because our sample size is so high, maybe this isn't the most helpful or detailed information. So we should probably use additional methods to see what exactly is going on with these data. So now let's talk about descriptive methods, which might give us some more detail beyond the inferential methods. So there are a couple different descriptive statistics that we can use to determine the nature of the data and how the data may differ from a normal distribution. The most common statistics that we use for this are skewness and kurtosis. So first of all, skewness is a measure of the distribution symmetry. So if we think back to the first example that we saw with that normal distribution, it has that nice symmetrical bell shape where the values are kind of symmetrically distributed around the mean. So the skewness measures the symmetry of the distribution. So how well or how symmetrical is the distribution around that mean or center? And so values of skewness can be either positive or negative. So higher positive values indicate that a distribution is skewed in the positive direction or skewed right. And negative values indicate that a distribution is skewed in the negative direction or skewed left. And values closer to 0 indicate that the distribution is closer to a normal distribution or is more symmetrical. And a general rule that you can follow is that values of skewness that have a magnitude greater than 2, so values greater than 2 or values less than -2, indicate high skewness. And so now let's talk about kurtosis. So whereas skewness measures the symmetry of the distribution, kurtosis measures the height of the distribution. So higher values of kurtosis indicate a distribution with a higher center peak, and lower values indicate a flatter distribution. Now, it is possible for values of kurtosis to be both positive and negative as well. But in general, a rule is that values greater than 3 indicate markedly high kurtosis. And kurtosis is important because if you have a distribution that has a very high center peak or a lot of values clustered near the mean, then that distribution may be more heavily influenced by outliers. So a distribution with high kurtosis or is highly kurtotic may be more susceptible to the effects of outliers. And then finally, other than skewness and kurtosis, another way we can possibly determine descriptively if data are different from normal is to look at the mean versus the median. And in case you don't know what the difference is between the mean and the median is, the mean is the arithmetic average value of a distribution, whereas the median is the center value, which is the value that occurs in the exact middle of the distribution if you were to arrange all of the values in order from lowest to highest. And so a distribution with a mean that is markedly different from the median may not be normal. So if you have a distribution, for example, where the mean is much higher than the median, then that might indicate a distribution that is positively skewed. So you might have outliers that are pulling the mean in the positive direction. Or you could have the opposite case where you have a mean that is much lower than the median. In this case, you may have outliers or extreme values that are pulling the mean of the distribution in the negative direction. And so let's take a look at some examples of what these descriptive statistics might look like. So again, I have our data set here that has 1,000 participants, and I ran descriptive statistics on these different variables. And this gives us a lot more detail than the inferential test did about the possible shapes of the distributions. So we see here for this variable that I've labeled normal, we actually see that even though that Shapiro-Wilk test was significant, we actually see that the values of skewness and kurtosis are quite low. And we also see that the mean is very close to the median. In this case, we have a median of 100 and the mean is almost, it's 99.84, very close to 100. So this tells us a very different story than the Shapiro-Wilk test showed us. And we can also see examples of how the skewness and kurtosis values can differ for our different variables. So we see down here, for instance, this variable that I've labeled as high skew. We actually see it has, relatively high skewness and very high kurtosis values to indicate that this might be a very highly skewed distribution. So these are just some examples of what you might see if you run descriptive statistics and get these descriptive measures of skewness and kurtosis that give us information about how the data are distributed. And so what are the advantages and the disadvantages of these descriptive methods? Well, first of all, one of the pros is that the descriptive methods provide an objective numerical value. So it provides a value for skewness and a value for kurtosis that we can interpret. And better than the inferential methods, it provides us some information about the distribution shape. So it gives us a lot more information about if the distribution is skewed, in what direction is it skewed. It also can give us information about the distribution height. It can give us information about if outliers may be present. And as opposed to the inferential methods, these descriptive methods are useful even with high sample sizes. So you can still interpret the skewness and kurtosis and the mean and the median, even if you have a very large sample size. Whereas with the inferential tests, once we get to very large sample sizes, those results are a lot less meaningful. However, there are some disadvantages to descriptive methods, and those are that the appropriate cutoffs for skewness and kurtosis are subject to debate. So depending on exactly what statistic reference you're looking at, they might suggest different numbers. And here we suggested a cutoff of 2 for skewness and a cutoff of 3 for kurtosis, but different references or different reviewers even may have different ideas about what constitutes high skew or high kurtosis. And while these reveal some information about the shape of the distribution, it doesn't give us a perfectly clear picture of the distribution shape. We still don't know exactly what the distribution looks like. So this is where visual methods come in. So this is the last type of method for assessing normality. And there are 2 main visual methods that we can use. One is histograms, which is what we saw earlier, which shows us that bell shape. And so a histogram shows the frequencies of the values in a distribution. And if we see that those frequencies follow a symmetrical bell shape, then that indicates that the distribution is normal. However, another visual method that we have are QQ plots. And in a QQ plot, we plot the values of the distribution versus expected normal values. And if we see a straight diagonal line in this plot, that would indicate that the distribution is approximately normal. And there are different advantages and disadvantages to these visual methods as well. The advantages are that the visual methods provide us a much more clear picture of distribution shape and give us a lot more detail about the nature and the severity of skewness or other deviation from normality. So it helps us essentially have a much greater idea about the nature of the data and the severity of any deviations from normality. However, the main disadvantage to visual methods is that their interpretation is subjective. So you actually have to look at these graphs and plots and make a subjective determination of, is this, does this look severely skewed or not? It's more of an interpretation rather than just looking at a number and having a cutoff that you can compare against. And so let's look at some examples of what these visual plots look like. So in this example here, we see data that are approximately normally distributed. And at the top, we see an example of the histogram where we see that symmetrical bell shape. And then below that is the QQ plot. And we see that the points on that QQ plot are following a pretty straight diagonal line with very little deviation from the diagonal line. So this is what these plots would look like if you're dealing with more or less normally distributed data. But what happens when it starts to deviate from normal? So let's look at some examples of this. So in this example, we see data that are positively skewed or skewed to the right. So we see in the graph at the top with the histogram, we see that the data are not symmetrical. We kind of see that bell shape, but it's shifted over to the left side of the distribution. And we have less frequent values pulling the distribution in the positive direction or pulling the distribution to the right. So we see that tail forming, that asymmetric tail forming on the right side of the distribution. And then in our QQ plot on the bottom, we see that the data are no longer following that perfect straight diagonal line. We're starting to see some curves or some waves in the points in that plot. And so a good way to interpret these Q plots is that, the bigger the waves or the curves or the more curvy the plot is, the more different it is from normal. You really want that QQ plot to follow as straight of a line as possible. So the more curves you see in it, the more different it is from normal. And we can see another example here, this time with data that are negatively skewed or skewed to the left. So we see at the top, we see our histogram. Again, the majority of the data are centered around the right side of the distribution, and we have less frequent values in the negative direction pulling the distribution to the left. So we have that asymmetrical tail pulling it to the left. And again, we see in our QQ plot below the curviness of those points on that plot, indicating that the data are deviating from normal. And now finally, here's a more extreme example where we see in our high skew variable, we see that this variable is very severely positively skewed. We can see that from the histogram, and we can also see that in the QQ plot, where in the QQ plot, that is not following a straight line at all, and it has almost a full 90-degree bend in the points. So we see how we can look at that QQ plot and know that that data are definitely not normally distributed. So those are the different methods that we can use to test for normality. So we talked about the inferential methods, the descriptive, and the visual methods, and what the advantages and disadvantages of those methods are. And as we can see from those methods, a lot of the times it's good to use a combination of those methods rather than just one method to test normality. So like we saw with the inferential tests, that doesn't always give us the best picture of the data. So we might want to supplement inferential tests with something like a descriptive or a visual method to get a better idea of how the data are distributed. But when we use those methods to assess our data, and if we see that that data is different from normal, and if that's a problem for our analysis, then how do we address that? Well, there are a couple of different methods that we can use to potentially address non-normal data. One simple method that we can do is to remove outliers. So if you have just a few extreme points that are pulling your data in either the positive or negative direction, for instance, and it's really just those few points that are causing a problem and the rest of the data are relatively normally distributed, then it may just be a simple matter of removing those outliers. So we can look at an example of how that plays out. I'm going to go into our software here, and I'm going to take a look at this last variable down here that I've labeled out. And we can see that this variable has very high skewness and very high kurtosis. So this data might not be normally distributed. And we can quickly look at a histogram of this variable. So we can look at our out variable, and we can see here that, yes, we see a positively skewed distribution, but it looks like maybe there are just a few points out here that are causing the problem. And maybe if we took those out, then our data might be closer to normal. So let's see what happens when we remove those outliers. So I'm just going to use this option over here to remove our outliers from this out variable. And then if we go back to our histogram and look at the variable with the outliers removed, we see that this actually looks very much closer to normal than it did before we took out the outliers. And we see that the values of skewness and kurtosis have also decreased very significantly. So this is just an example of how we can fix a problem of non-normality simply by removing outliers. So another method that we can use to address not normal data is a data transformation. So sometimes, depending on the exact nature of the data, it may not be possible to fix the problem simply by removing a few outliers. You may have to do a complete transformation of the data to get it to look closer to normal. So there are different transformations that you can use. Common ones include the logarithmic power or root transformations, such as taking the square root or the cube root of the variable, or taking the reciprocal or the inverse of the variable. And these different mathematical transformations can sometimes fix the problem of normality and make the distribution look closer to normal. So using this transformation option in our software, we can look at how these different types of transformations can affect our data. So let's just, for example, take a look at, let's say, our right skew or positively skewed data and see how these different transformations might influence the shape of the data. So we see here with the logarithmic transformation, maybe that gets us a little bit closer to normal, still looks maybe a little bit skewed, and we can see, the values of skewness and kurtosis are actually improving, getting closer to 0 with this transformation. So maybe that's helping a little bit. And we can look at different things like square root. Maybe that one's not as good. Reciprocal looks like it actually helps quite a bit. And then can look at things like cube root, squared transformation, or cubic transformation. But it looks like in this case, maybe the reciprocal transformation gets us a lot more close to normal. So we see our skewness has gone down significantly. Maybe our kurtosis has gone down, but it's now in the negative direction. But we can see that based on this histogram, we're seeing data that look closer to normal than it did from the original variable. So this is just an example of how we can use transformations like this to make the data look closer to a normal distribution. However, the main disadvantage of using something like a transformation is that you're now, instead of looking at the raw variable in your analysis, you're looking at the effects of the transformed variable. So that might affect your interpretation of the results. If you're doing something, especially like a regression, where you're looking at prediction, you then have to look at prediction of that variable in terms of its transformed version rather than its raw version. So transformations like that can affect how you interpret your results. So that's just something to keep in mind. Although transformations can be useful in correcting normality, it may affect how you interpret things. And finally, the last method, and what may be the best method for addressing non-normal data, is to run a non-parametric test. So we discussed at the beginning how it's parametric tests like the t-test or the ANOVA or linear regression that assume normality. And that's why it's called a parametric test, because parametric means it is based on a specific distribution. However, a non-parametric does not assume anything about the distribution of the data. That's why it's called non-parametric. And so you can run a non-parametric test on data that are not normally distributed, and that doesn't cause any problems because there are no assumptions about normality for those tests. And the good thing is that a lot of the common statistical tests that we use, such as t-tests or ANOVAs, have a non-parametric version of that test that we can use in case we have a violation of an assumption like normality. So for instance, like in independent samples t-test, the non-parametric version of that test is the Mann-Whitney U-test, and it'll give us similar output in terms of, you run your test and it gives you a p-value to determine if two groups are significantly different from each other. But the non-parametric version of the t-test, or the Mann-Whitney U-test, does not assume that the data are normally distributed. And then there are non-parametric versions of ANOVAs. There are also non-parametric regressions that you can conduct. So instead of a linear regression, you can conduct a logistic regression, such as a binary logistic regression or an ordinal logistic regression that doesn't assume that the data follow a normal distribution. So if something like removing outliers doesn't work, or transforming the data doesn't work, or if you'd prefer not to transform the data, then you could probably run a non-parametric test to still be able to run an analysis that will answer your research question, but you don't have to worry about normality and possibly other assumptions that may be violated as well. Okay. And so that takes us to the end of our presentation. So again, if you are interested in additional support beyond this webinar, if you're interested in more one-on-one support, we do have services available that you might be interested in. So you can use this information to contact us and get more information about the services and additional support that we can provide. And with that, I will see if we have any questions, and I will open things up to questions now. So if you do have questions, you can feel free to type those into the question section now. Okay, so let's look at some of these questions. So one question is, do you find that Shapiro-Wilk with large sample sizes tends to deliver more type 1 errors due to sensitivity, making visual test better? And yeah, and we kind of covered this in our discussion of the pros and the cons of the different methods. It is definitely true that as the sample size gets larger, the Shapiro-Wilk test and other inferential tests become less and less useful to us because those will basically always turn out to be significant at large sample sizes. So really, once you get beyond, like you suggested, n greater than 50, or even, once you get into n greater than 100 or 200, the Shapiro-Wilk test is almost always going to be significant. So it is better to use something like a descriptive method or a visual test in that case. The next question is normality needless with Pearson's R since the data is so robust? A lot of people will say that you do need to test normality with a Pearson correlation. Like there are some references that'll say you should test normality with the Pearson correlation, but really with the Pearson correlation, the main concerns about the correlation are that the data need to be linear. So the main concern with the Pearson correlation is if your data, a relationship was nonlinear. That's probably a little more important than normality. And again, the statistics that the significance testing for Pearson is based on tends to be robust towards little deviations from normality. But if you're dealing with data that are very severely skewed or deviate very severely from normal, that might be something to be concerned about. So you may want to consider, in cases where you have very severe deviation from normality, something like a non-parametric correlation, like a Spearman correlation. Okay, let's see if we have any more questions here. So the question is, what is the non-parametric alternative to ANOVA? One of the, it kind of depends on which type of ANOVA that you're doing. If you're doing a one-way ANOVA, or in other words, a between subjects ANOVA, or a within subjects or repeated measures ANOVA. So the alternative to the regular one-way ANOVA that looks at differences between subjects is the Kruskal-Wallis test. So you can actually go into our software and look at our list of non-parametric tests over here. So in our software, we have a full list of non-parametrics, and we see here we have a Kruskal-Wallis test that tests the differences between an outcome on a nominal level variable. And then the repeated measures ANOVA, the non-parametric version of that is the Friedman test. So that's if you're looking at differences between two or more repeated measurements, then the non-parametric version of that test is the Friedman test. Okay. And it looks like those are all of the active questions that we had so far. If anyone has any other questions, then you can feel free to type those into the question section now. I'll give just another minute or so in case anyone else has any additional questions. Okay, it looks like we don't have any other additional questions coming in, so I'll go ahead and end our webinar for today. And again, you can use the information that you see here to contact us if you're interested in more support, or you can look at our list of upcoming webinars if you're interested in webinars on other topics. So thanks everyone for attending our webinar today. I hope everyone found this useful, and I hope everyone has a great day.